Hello students, welcome back to another exciting episode of Conic sections. We've already met the circle, the ellipse, and the parabola, three of the coolest curves in mathematics. And today, meet their rebellious cousin, the hyperbola. Unlike the circle that likes to stay closed and perfect, or the ellipse that keeps it elegant, the hyperbola is like, hey, I'm too open for that. Literally open. It has two separate branches that just can't stay together. So, what's the math behind this dramatic personality? Well, here's how we define it. A hyperbola is the locus of all points P in a plane such that the absolute difference of their distances from two fixed points f1 and f2, called the foci, is constant. That means the distance pf1 minus pf2 in absolute value is equal to 2a. So we write mod bracket pf1 minus pf2 bracket close equals 2a. And the line joining f1 and f2 is called the transverse axis. A line through the center, perpendicular to it, is the conjugate axis. The midpoint of f1, f2 is the center, and points at a distance, a, on either side of the center are called the vertices. Think of the hyperbola as two branches that had a disagreement. They move apart but mirror each other perfectly. Let's set up our coordinate system. We place the center of the hyperbola at the origin. That's the point 0, 0. The foci are located at minus c, 0, and c, 0. For any point P with coordinates x, y on the curve, the difference in distances from the two foci is constant, and that constant is 2a. So, the equation of the hyperbola comes directly from this definition. After some algebra, and yes, quite a bit of squaring, we get the standard equation. X squared by squared minus y squared by b squared equals 1. The relationship between the parameters is c squared equals a squared plus b squared. That's an important one to remember. For a circle or an ellipse, we have c squared equals a squared minus b squared. But the hyperbola says, nope, I'm the opposite. C squared equals a squared plus b squared. The eccentricity, which measures how stretched the curve is given by E equals c by a. And since c is greater than a, E is always greater than 1. So remember, the ellipse was shy with E less than 1. The parabola was perfectly balanced with E equal to 1. But the hyperbola? The overachiever, always E greater than 1. Now, not all hyperbolas like to lie flat. Some stand tall. If the transverse axis lies along the y-axis, the equation flips. Y squared by squared minus x squared by b squared equals 1. If the hyperbola isn't centered at the origin but at some point h, k, its equation becomes x minus h squared by squared minus y minus k squared by b squared equals 1. In general, any conic section can be represented as a x squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And here's a neat trick. For a conic to be a hyperbola, the discriminant must satisfy b squared minus 4ac greater than 0. That's your ID check for a hyperbola. Think of it like this. If b squared minus 4ac is positive, the conic says, yep, I'm a hyperbola. Now let's talk about something that gives hyperbolas their trademark look, the asymptotes. These are the lines that the branches of the hyperbola approach but never actually touch. For the standard form x squared by squared minus y squared by b squared equals 1, the asymptotes are given by y equals plus or minus b by x. As x becomes very large, the curve gets closer and closer to these lines but never meets them. The rectangle formed with sides 2a and 2b helps you draw the asymptotes. Its diagonals are those very lines. Latus rectum. That's the chord through the focus and perpendicular to the transverse axis. Its length is given by 2b squared by a. So if you know a and b, you can find almost every other property. C, eccentricity, asymptotes, and even the latus rectum length. Quick recap. C squared equals a squared plus b squared. E equals c by a. and asymptotes y equals plus minus b by x. Let's return to where it all started, the foci and the directrix. For any point P, x, y on the hyperbola, the ratio of its distance from a focus to its distance from the corresponding directrix is constant. That is, PF divided by PD equals E. And remember, here E is greater than 1. The equations of the directrices are simple. X equals plus or minus a by E. The bigger the eccentricity, the more the branches open up. And as it gets just a bit above 1, the hyperbola starts to resemble a parabola. In physics, hyperbolas show up in radio navigation, where signals from two stations reach you with a constant difference in distance. And guess what? That path is a hyperbola. Alright, time to get our hands a bit dirty. Let's derive the hyperbola's equation from its definition. We have foci at minus c, 0 and c, 0. For a point P, x, y on the curve, PF1 equals square root of bracket x plus c squared plus y squared, and PF2 equals square root of bracket x minus c squared plus y squared. Now, from the definition, mod bracket PF1 minus PF2 bracket close equals to A, assume PF2 minus PF1 equals to A for the right branch. So, square root of bracket x minus c squared plus y squared equals to a plus square root of bracket x plus c squared plus y squared. We square both sides, simplify, then square again to eliminate all radicals. After some algebraic patience, we arrive at x squared by squared minus y squared by b squared equals 1, where b squared equals c squared minus a squared. Yes, that's a lot of algebra, but it's pure beauty, all starting from geometry, ending with a clean algebraic form. Let's bring everything together. Example, for x squared by 9 minus y squared by 16 equals 1, a equals 3, b equals 4, so c equals square root of a squared plus b squared equals 5, and e equals c by equals 5 by 3. That means foci are at plus minus 5, 0, asymptotes are y equals plus minus 4 by 3 x, and the latus rectum is to be squared by equals 32 by 3. Common mistakes to avoid. Mixing up a and b. Remember, a is always along the transverse axis. Forgetting that c square is equal to a square plus b square, not a square minus b square. Writing E1 always. Verification checklist. Vertex A, 0 must satisfy the equation. Foci are at plus minus c, 0. Asymptotes. Y equals plus minus b by x. So here's the big picture. All conics, circle, ellipse, parabola, and hyperbola are part of one family. They differ only in eccentricity. Circle has E equals 0, ellipse has E1. It's like the family reunion of curves. The circle is calm, ellipse is classy, parabola is perfect, and hyperbola? The dramatic overachiever, always going to infinity. And that, my friends, is the hyperbola, the curve that defines openness, balance, and beautiful symmetry.